Okay, so last time we introduced semi-log canonical singularities. So we had pairs x comma delta that were not necessarily normal, but they were reduced S2 and nodal in codimension 1. And sometimes a variety that satisfies these properties is called demi-normal. It's pretty close to normal. And in this case, in this demi-normal case, let me use a different color again. What we saw was that if you look at the normalization, then we had this conductor, and the vanishing of the conductor was a divisor on xn, and was also a subscheme of codimension 1 on x. So on x, it's this double locus, or the non-normal locus. And on xn, it's the preimage of the double locus, which maps 2 to 1 to D, which is why we call it the double locus, because we're assuming it's nodal in codimension 1. So it's generically a 2 to 1 map. So here it's generically 2 to 1. And this is a closed subscheme of xn. And the observation is that the pullback of kx plus delta is equal to kxn plus delta n, just means the pullback of delta to xn, plus this double locus. And so this was this double locus is the right divisor to include if we're talking about singularities with the pair x comma delta. So then the second part of the definition is that the pair xn delta n plus this double locus is log canonical. And then finally, the third part of the definition is something we just need all the time whenever we're working, because we want to work with intersection products. We need to know that kx plus delta is Q Cartier. Okay, so this is our definition of semi-log canonical singularities, and we came at it from the point of view of what's the minimum we need to work with divisors and to talk about discrepancies, and what occurs when we have a integral divisor with coefficient 1 inside of our log canonical pair. So that's where we got the fact that it needed to be nodal in codimension 1, but also it works out because when it's nodal in codimension 1, it makes sense to talk about the pair delta n plus dn, because dn is then a reduced divisor. Well, if you had worse singularities in codimension 1, dn might have coefficients larger than 1, and then this pair is not a well-behaved log pair. Okay, and then now we can talk about stable pairs, which is the non-normal version of log canonical models. So, and we'll see later in the class why people sometimes use this word stable pairs, but this is just, you should think of it as semi-log canonical model. And let's abbreviate semi-log canonical as SLC. So a stable pair, x comma delta, if one, it has SLC singularities. And two, the log canonical is ample. So just like in our case of a log canonical model, the log canonical model has log canonical singularities and the log canonical divisor is ample. Here, a semi-log canonical model or a stable pair is a pair that has SLC singularities, and kx plus delta is an ample Q Cartier divisor. Of course, this Q Cartier condition is already built into the SLC singularities part, but we'll see in a second that it's actually a little subtle to determine when kx plus delta is q Cartier, so I wanted to repeat it for emphasis. Okay, any questions about those definitions? Okay, so so now the idea is to work with these stable pairs by using this diagram that I drew here that relates the stable pair to the normalization and the double locus, because that's how we talk about even discrepancies. This is also how we can talk about the ample condition. If we know that kx plus delta is q Cartier, then we can check that it's ample by pulling back to this normalization. So with one caveat, let me think. So I believe there are some weird examples where, yeah, there are some weird examples where it's not enough to check that the pullback to the normalization is ample. But here I think they're ruled out by the Q Cartier condition. So what you can do, yeah, here's a strange example. If you take P2 and you take a conic in P2 and a line in P2, and then you glue them together. So you identify a conic and a line are both P1s, and so you identify them. Then you get some diagram like this where P2 is the normalization and the union of the conic and the line is your dn. And I believe in that case, yeah, in that case, the canonical divisor downstairs. What do I want to say? Oh yeah, what I want to say is that quotient is not projective. That's what I want to say. That quotient is not projective. It's that like, so it doesn't have any ample line bundles. And the reason it's not projective is because if it had some ample line bundle, you took some hyperplane and you pulled it back, it would be an ample line bundle upstairs, but it would have different intersection number with the two components of the double locus, and that would be contradiction. So anyway, so my point is that kind of descending these ample line bundles is a little subtle. You have to worry about you have to worry about the intersection of the double locus, but we'll see that that under our conditions, if we can guarantee that kx plus delta is q Cartier, then we can check that it's ample on the normalization. Sorry if that was a little confusing. Okay, so let me draw this diagram again. Because we have this generically 2-to-1 map from dn to d, we have an involution on dn. We'll call it tau, but it's just it's only an involution generically, and we'll see examples where there might be points where dn to d is not 2-to-1, and there you don't have an involution anymore. But wherever it's 2-to-1, you have this involution that just swaps the two fibers. And the other observation about this diagram is that it's a push out. So if you ever thought about pushouts in schemes, they're actually quite delicate. But these type of diagrams where you have closed embeddings as your horizontal maps and a finite morphism as your vertical map, these type of diagrams, the pushouts exist. And a normalization with the conductor is always an example of a pushout. So another way to think of the conductor is that it's the unique ideal such that this diagram is a pushout. And so what we want to do is say that we can reconstruct our semi-log canonical pairs by looking at the data of xn, dn, and this generic involution tau. We want to say, draw this diagram, reconstruct d, take its push out. That's the semi-log canonical pair. So to illustrate some of the difficulties with this, I want to draw some examples. And again, the main difficulty is this Q Cartier condition. So example 1, let's say we have two planes glued together along a line. And let's say for our divisor, we took a line on one of the planes. So here's delta. Then when we normalize, we separate our two planes. And now we have our double locus is just a line on each of them. So this is D. Our involution just swaps the two lines. In this case, the involution is defined everywhere. And then our delta n, or sorry, this should be dn, since in my notation, D was the double locus downstairs. And then our delta becomes a delta n up here, which is a different line on one of the two components. And now the point is that this x, it is demi-normal. It's reduced S2 nodal in codimension 1, in fact, just nodal. And it is true that the normalization with the double locus plus the pullback of our boundary divisor is log canonical. But it turns out that kx plus delta here is not Q Cartier. And the way we see that is, again, the same idea as what I said in words before about this example of a push out of a projective variety that was not projective, is that if we look at kx plus delta, if it was Q Cartier, then it'd have a well-defined intersection number with D. But we can compute that intersection number because D is some curve. But we can compute that intersection number by pulling back and restricting to the preimage of D by the projection formula. As long as we take one of these two divisors by the projection formula, we can compute that intersection number by looking at the preimage. And if we compute the two different ways, because we have these two different components, so we got two ways of computing, we can pull back kx plus delta and restrict to the first component. I'll call D1n. So D1 will be the one on the left, and D2 will be the one on the right. And these two components are swapped by the involution. Then here we have kx plus dn, so kx normalized plus d normalized plus delta n restricted to d1. So here we see one of the advantages of these of being nodal in codimension 1. When we do these type of computations with a double locus, we automatically get the double locus appearing here, so we can apply a junction. So when we apply a junction, we get k d1n plus everything's normal crossing, so it's just the restriction of everything that's left to d1, but there's no other divisors in a neighborhood of d1, so it's just plus 0. And so the intersection here is the canonical of d1. Well, that's some line, so this has a degree -2. On the other hand, if we pull it back the other way, well, now we get the canonical of d1, but now the different is not of d2, sorry, but now the different is not 0, because now we have this component delta n that intersects d2. So here we actually get plus a point, whatever this point of intersection is, and this has degree -1. And these two numbers are different, and they would have to be the same if kx plus delta was Q Cartier, because they would just be equal to the intersection number of kx plus delta with d. And so this tells us that at least a necessary condition for kx plus delta to be Q Cartier is that the different on each of our components of the double locus when we normalize is the same. But that's not so precise, because here I chose an example where it turned out that the double locus split up into two components and the involution just swapped them. But more generally, that doesn't have to be the case. The double locus can just be something like an elliptic curve inside of P2, and you take a hyperelliptic involution on the elliptic curve and glue by that. And there, the double locus isn't two components, it's one component, but it just happens to be swapped by an involution. So the more precise way to say it is that a necessary condition for Q Cartier is that the different of dn is tau invariant. So in this case, when we look at the whole dn rather than just the two components, the different is the point p on component d2 plus the divisor 0 on component d1, and that's not tau invariant because when we apply tau, we get a point on d1. So this is a necessary condition for Q-Cartier, and this comes up even when we don't have a divisor. So here's example 2. I won't write down the details, but you can check if you take a cone and you take a plane and you glue these along a line in the plane and a ruling on the cone. Well, we computed here the different on the cone, and the different on the cone is half a point. But the different for the line and the 0 divisor is just 0. So if we were to glue these two together, we'll get something that's demi-normal nodal in codimension 1, whose normalization is log canonical, but the canonical divisor is not Q-Cartier. So here we have no boundary when we glue. So if this is xn comma dn, then we glue these to x, and here kx is not Q-Cartier. For the same reason. Okay, so that was one issue, and then the other issue is that this tau doesn't have to be a morphism; it just has to be a rational map. So here's an example where the involution does not extend to the double locus. If you take, so I'll apologize for my bad drawing skills. We want to take just xyz equals 0 in A3. So we have our 3 planes intersecting something like that. And when we normalize this, we get a union of 3 planes. What's the double locus? Well, the double locus are the coordinate axes inside of each plane. So let me use some color coding. So the normalization is 3 planes. The double locus, let me make sure I match these up right. There's a component, the horizontal, like this axis gets glued to that axis. This one gets glued to this one, and this one gets glued to this one. So if we take this picture of 3 planes with the coordinate axes as our divisors, and we take the involution that swaps them according to these colors, that's what gives us x. But note that this involution can't be defined at the origins of the planes, because the origins of the planes, do you send the origin, do you swap the blue curves, or do you swap like the green curves or the purple curves? So however, if you look at this picture, tau is defined on the normalization of the double locus. If we now take these 3 nodal curves and normalize them, then we'll get just 6 lines, and now the involution does extend because now we've separated the nodes. And so now the node on the blue point will go to the node on the blue point, but the node on the green point to the green one, etc. And now, just because we're running out of notation, we'll call this the normalization of dn. And so we have an actual involution on the normalization, and so now we can modify our diagram a little bit, and we can say that if we take in the data of a log canonical pair x delta n plus dn, and an involution tau from the normalization of dn to dn, with the property that tau preserves the different. So we can talk about the different on the normalization. Then we can ask, if we have the data, such data, can we reconstruct a semi-log canonical pair? So this is the data we know that we have if we start with a semi-log canonical pair, and now we want to go backwards. And what you want to do is just take the diagram analogous to the push-out diagram, but with this normalization now. Then we have this involution, so we take the quotient by the involution, and we want to just say that we can fill in this diagram to produce our x. But the issue now is with the normalization, this map is no longer a closed embedding because we've normalized. And it turns out these pushouts just don't exist in the category of schemes. So you have to work harder to actually construct your x, and actually it's quite difficult to do this, but this was achieved by Kolar. So if I summarize, basically, one, such quotients exist. Here you have to be a little careful about what exist means, but such quotients exist in the log canonical case. And here, what do I mean by quotient? Because it's not a pushout. Well, I mean that there's still an equivalence relation on xn generated by this dn bar and this tau. And the equivalence relation is that two points of xn are equivalent if and only if they're in the image of an orbit of tau. And so that's not a pushout. So it turns out that that's not a pushout equivalence relation, but it's still an equivalence relation. And quotients of schemes by equivalence relations are also very subtle and most of the time don't exist. But it turns out that in the case where you actually start with a log canonical pair and this involution is defined on this divisor with coefficient 1 on your log canonical pair, then Kolar shows that such things exist. A priori, they're only algebraic spaces, and if you don't know what an algebraic space is, that's okay. And here he really has to study the behavior of log canonical centers, and he has to stratify the variety xn in terms of its log canonical centers and understand how tau interacts with these log canonical centers to produce this. It's quite subtle. And then the other observation is that, or not the other thing he proves, is that the this condition on the different is sufficient. So kx plus delta is Q Cartier. Or another way to say it is that the log canonical divisor on xn descends to a Q Cartier line bundle on x if and only if the different is tau invariant. And now finally, again, there's this issue of what does exist mean. But once we descend the Q Cartier divisor, then we can ask for it to be ample. And if it's ample, then we have something projective automatically. So we don't have to worry about which category it exists in. And so then the full theorem that he proves is that there's a bijection between semi-log canonical stable pairs. So if we do assume that some ampleness for kx plus delta, and triples of a log canonical pair delta n plus x comma delta n plus dn, such that kxn plus delta n plus dn is ample, along with an involution that preserves the different. Okay, and the point is just that once you've descended your divisor some Q Cartier, then you can check that it's ample, and so you get something that's actually a projective variety that's semi-log canonical and stable. Okay, so this tells us that the way that you want to study stable pairs, or more generally semi-log canonical pairs, is to normalize them, study something there, and then hope that it descends under Kolar's gluing. to the semi-log-canonical pair. So okay, any questions up to there? So let me write that in words. So then if you want MMP for semi-log canonical pairs, namely what you really want to do is compute the semi-log canonical model. So you want to say if I input a semi-log canonical pair that's not stable, then I want to run MMP and produce a stable model for it. So the kind of strategy suggested by this gluing theory is so we input x comma delta, which is SLC. We take the normalization. Then we run MMP on the normalization to get a log canonical model. I guess here we're in the absolute case. I just got so used to writing over B the last few lectures. So to take the log canonical model and then reglue. Okay, so that's strategy. It turns out this just completely fails. And the issue is exactly this fact that the different is preserved by your involution. There's no reason for this to be for this property to be preserved when you run the MMP on the normalization, and in fact, it's just not preserved. So the easiest example to see what goes wrong is if you take maybe I should write down in the notes. This does not work in general. Oh, I don't know what I did. Okay, so the easiest example is to take the union of two planes again along a line. Well, sorry, not two planes. The unions of two smooth surfaces. They can't be planes, as we'll see in a second. So take the union of two smooth surfaces and suppose that, so this is D, so we're gluing this together. And suppose that we have another divisor delta over here that's just disjoint from D. Since this is disjoint from D, then the different condition is satisfied because the difference is just 0. Assume D is Cartier. So then when we glue these, we get some nodal union like this, and we just have a divisor here. But now the MMP on the normalization doesn't care at all about the glued thing, and it's possible that there's some curve, some horizontal curve, such that when you that gets contracted by the MMP, and when you contract it, suddenly delta and this purple divisor intersect after that contraction. So, for example, if you take this to be P2 and this to be the blow up at a point of P2, and the two curves are kind of going through the exceptional divisor. Then when you take the log canonical model there, you'll have to blow down this exceptional divisor. And so when you blow that down, of course, here I should have maybe added some extra divisors that are just disjoint from everything to make things stable, because or you can, instead of P2, take some surface of general type, but with the same kind of local picture. But we'll ignore that. So when you run the MMP, you have to blow down this this exceptional curve, and so now you'll get on one component just nothing changes, and on the other component we've blown down a curve, and now delta and D intersect. And now we're in this example where the different is not the same on the two points. So here, when we glue them together, we get something where K is not Q Cartier. So this is, we'll call this X0n, and here we have X0 when we reglue, and here KX0 is not Q Cartier. Okay. And it's even more serious than that, because you might say, well, maybe there's some strategy, we can modify our strategy to make it work. And in general, you actually just can't. There are examples due to Kolar where the log canonical ring is just not finally generated. Even in dimension 2. And of course, if we could run the MMP and produce a semi-log canonical model or stable model, then that would imply finite generation. So this just tells you in general, just can't work. But this picture also suggests one situation where it does work, and this situation is the one that's important for moduli. Let me move this down so I can draw the picture right below. So imagine for a second that this surface X was sitting inside of a threefold, and this surface was one of our boundary divisors. And imagine that this contraction of this curve that made the delta and the purple curve collide was actually a flipping contraction of our threefold. Then in that case, we're not actually done with X0. We then have to produce a flip. And when we produce a flip, well, what is it going to look like? It's going to look like, when we produce a flip and then restrict to this particular divisor inside of our threefold, then we're going to have produced a new curve from our flip. Let me draw it here. And now we will have the strict transform of the purple curve. And will be glued together like this. Here's our other component. Oh, here we're in the non-glued side. So then our other component will be the same thing. And now that we've introduced this flipped curve, now we can hope that the difference are the same, because now we have this extra divisor, this red piece. I'll call it X plus or something for the notation for flip. So now when we glue, it'll look something like this. Okay, and the upshot is that if you are in this situation, then this X plus actually will be semi-log canonical, i.e. Kx plus will be Q Cartier. So somehow the point is that this happens because there are hidden flips that you only see if your variety comes embedded inside of a KLT, say, threefold or KLT n plus one fold, and that your steps in the minimal model program are actually coming from the MMP on this higher dimensional variety. And whenever you have this situation, then by looking at this higher dimensional variety, you see these hidden flips, and now you've kind of fixed this this issue with the different. And so the upshot is that actually all these examples of Kolar are not, they're not smoothable. They don't sit inside, they don't sit as, say, Cartier divisors inside of some higher dimensional KLT pair or DLT pair. Okay, and it turns out, thankfully, that this is, for most applications, this is good enough. This case where you're actually inside of a higher dimensional variety. And in fact, what we said was that this is one of the motivations for looking at semi-log canonical pairs in the first place, is that if we had some log canonical variety and we wanted to do induction to study MMP on our log canonical variety, then our divisors don't have to be normal if our variety is strictly log canonical. So we showed kind of in the DLT case, all these divisors with coefficient 1 are normal, but not in the law canonical case. So let me just emphasize that. Let me write down this as a lemma. If x s plus delta is log canonical, such that the round down of s plus delta is s, and such that, well, and let me say, suppose s satisfies Sayre's condition s2, then s comma the different is semi-log canonical. Okay, and this just follows directly from what we already know about a junction, because a junction tells us that when we go to the normalization of s, we get something log canonical. We're assuming s is s2 as part of the lemma, and we just need to check that s is nodal in codimension 1, but we already did that last time because we checked that for surfaces, these divisors with coefficient 1 have to be nodal curves. So in codimension 1, s is nodal. And I should say a word on this condition. You really have to, in general, you have to assume that your divisor is S2, but Alexeyev, he proved something more general, but at least maybe for most applications, the simplest statement is that if S is Cartier, which maybe is what you want for inductive arguments, because you'll say I'm going to slice by hyperplane sections, then it's automatically S2. But in general, it really doesn't have to be S2. But there are ways around this. You can try to find some S2ification or something. Okay. Any questions about that? Okay, so now we can start talking a little bit about moduli spaces. So moduli spaces of higher dimensional varieties. So let's just set straight what we will call a moduli space. So let's say we have some collection of varieties that we care about. For us, it'll actually be stable pairs, but I kind of want to motivate why, if you are studying moduli of higher dimensional varieties, you'll actually are almost forced upon this notion of stable pairs. So we have some collection of varieties, and now what's a moduli space? Roughly, well, we want a space M with a family X, pi from X to M, such that one, pi is a flat family of varieties in our collection. So let me give a name here. Let's call this collection C. 2, the points of M are in bijection with C, where the bijection is X maps to the fiber of X, which is a variety in our collection. And then 3, it satisfies some universal property. Okay, and kind of the nature of the universal property and the nature of what a space means here. So really, all these will be algebraic stacks, not necessarily schemes. That's all kind of beyond the point of this class. So I want to focus on constructing families that at least have every fiber that you want, and maybe you can just believe that they'll have some kind of universal property. Unless you're familiar with all this stuff, and then you already know what to do to fill in the details. Though I will say one of the difficult parts in higher dimensions is that the particular universal property, or another way to say this is represents a functor. The particular functor is actually quite subtle in higher dimensions. And that's actually one of the biggest difficulties for moduli of stable pairs. Okay, so with that very brief introduction to moduli spaces, what properties do we want M to have? I mean, you want to do algebraic geometry with M, so you can't do algebraic geometry with completely general spaces. You need some nice properties at least. So here's a checklist of wants for M. The first two are kind of, we don't want pathological examples. So one, we would like M to be separated. Non-separated spaces are quite pathological. We want to avoid that. Two, we want it to be finite type. Again, non-finite type spaces are pathological. If our collection is too large and we don't have something finite type, it might not even be algebraic because it might be just too big. Or in the literature, you'll see this referred to as bounded. People often talk about moduli functors being bounded. Three, well, if we have something that's separated and finite type, the next natural question would be, is it proper? And given the abundance of theorems in algebraic geometry that start with the assumption that something is proper, it's a good thing to want for your moduli spaces. And four, well, once we have a proper space, we can ask, is it projective? And again, there's an abundance of theorems that assume projectivity, so you'd want some projectivity if possible. And here, again, with the caveat of what we mean by spaces, here, if you know about stacks, then here we really can only ask for the coarse moduli space to be projective. Okay, and now the kind of upshot is that if you're studying moduli in higher dimensions, and you want 1 through 4, basically stable pairs, these semi-log canonical models, are exactly what you need to produce a moduli space. Okay, so first, let me recall the one-dimensional example, so we can see how it actually falls within the framework of semi-log canonical varieties and stable pairs. So so in one dimension, we can kind of classically people have considered MGN. So this is the space of pairs C P1 through Pn, such that C is a smooth genus G curve, and Pi are just some marked points. And here people assume that 2G minus 2 plus N is greater than 0. But now if we unravel this condition, what this really means is that the pair C, comma, the sum of Pi is an LCM, is a log canonical model. It's exactly the condition that the log canonical divisor, where the P1 through Pn were on a curve, marked points are the same as divisors. The log canonical divisor is ample, is exactly saying that 2G minus 2 plus N is greater than 0. And of course, for curves, we don't have to worry about birational geometry because there's just a unique representative, C itself. Here I should have said projective. There's a unique proper representative. And so MGN really is the space of log canonical models of one-dimensional pairs, of one-dimensional log pairs. And then this has this classical compactification due to Deline and Mumford, which is MGN bar. And here, Now you write the same thing, tuples C comma P1 through Pn. And normally people say you have C is at worst nodal, Pi are smooth points. So we're marking smooth points. Well, here still projective of genus G. And well, people give several conditions. Like they might say the automorphism group of the pair is finite, but really the condition is that the log canonical divisor is ample. And so kind of this very classic compactification from 1969 due to Deline and Mumford. In the language of what we just discussed, we can exactly phrase this as saying that MGN bar parametrizes the class of semi-log canonical stable curve pairs. Because we're assuming that the log canonical divisor is ample and C has at worst nodal singularity, so it's nodal in codimension 1. S2 is trivial because it's a curve, so it's reduced curves are automatically S2. Because there are no codimension 2 points. It's just Gorenstein, so it's Gorenstein in codimension 1, and the pair is, the normalization is just a smooth pointed curve, so that's log canonical. So this MGN, the upshot is MGN bar parametrizes stable pairs. Again, in our sense of log canonical, semi-log canonical models in dimension 1. And since these were classically called stable curves, that's why people use the word stable pair for higher dimensional semi-log canonical models. Okay, and the other upshot is that MGN bar satisfies everything we want. So now we want the same thing in higher dimensions. And now, kind of, if we didn't already go through the work of defining log canonical models and studying the minimal model program, and we were just thinking, okay, I want moduli spaces of higher dimensional varieties. So let's say I start with some family of smooth surfaces, smooth projective surfaces, and I want to construct their moduli space. And I want it to have properties 1 through 4. And that'll be the analog of MGN, or just MG, where I just have smooth guys. There's already an issue here. So let me just write it this way. The moduli of smooth projective varieties in higher dimensions. Of course, here I mean the word moduli loosely because we haven't proved anything exists. So just kind of the functor of smooth projective varieties, if you want. Kind of the naive thing you might look at is not separated if the dimension is greater than or equal to 2. And why is that? It's exactly because we have birational models. If you insist on parametrizing smooth projective varieties, then if you look at your families, you can take birational transformations of your families, and these give you different limits. So if you think about the valuative criterion of separated, what does the valuative criterion to be separated means? It says that if limits exist, then they're unique. And this just can't be the case if we try to work with all smooth projective varieties, because you can have the same family of smooth projective varieties have 2 different limits, 2 different birational models of the limit. So if you change birational models, then you lose uniqueness of limits. And so, of course, because we already learned about the minimal model program and we learned about log canonical models, we know how to solve this. We know, yeah, smooth projective varieties don't have a unique representative in their birational class, but they do have a unique log canonical representative, specifically the log canonical model. And so MMP implies that the analog of MG, where we haven't compactified yet, the space that we want that just corresponds to smooth curves of genus G, or if we add a divisor, smooth pointed curves of genus G, should be of log canonical models. This is a space of log canonical models of pairs x comma delta. And so to even make sense of this, we needed to know that log canonical models exist. But once we know that once we have BCHM and we know that log canonical models exist, then we can hope to construct the moduli space that parameterizes log canonical models of pairs of general type. Of course, we need to have log general type for there to be a log canonical model, and then go from there to compactify it. Okay, so that's the first observation, is that to get a separated moduli space, we need MMP and we need log canonical models. And now the second observation is how do we get properness of our moduli space? Well, actually, there's a few things. So this gives us separated. So let me label these. So one, this discussion gives us separated. We need to talk about boundedness. Why is the set of log canonical models bounded? Or another way to say it, why does there exist a finite type scheme, or variety, which has a family that contains every log canonical model? Well, in general, it doesn't, because even if we fix the dimension, already for curves, we saw that we need to fix more than just the dimension. We need to fix the genus and we need to fix the number of marked points. But then once we do fix the genus and the number of marked points, then we get this bounded moduli space for curves. So there's the question of what do you need to fix to get a bounded or finite type space of log canonical models? And this, in general, so in full generality, I think so in surfaces, this was in surfaces for the case of pairs, for the case of log pairs, for log canonical pairs, this was studied by Alexeyev, but in full generality, this is due to Haken, McKernan, and Xu. So the H and M from BCHM, and then also Chen Yang Xu. But building off of the work of BCHM and all the work around that, where they show that I mean, I think they show a more precise statement, but for the purposes of moduli, the statement is that if you fix the coefficient set of delta, so in particular, you also fix the number of components of delta, say, if we are doing if we're doing ordered, where delta is really a sum of di. But we'll ignore that for a second. So if you fix the coefficient set of delta, you don't let the coefficients just vary arbitrarily, and you fix the volume of kx plus delta, then the log canonical models of pairs of this fixed volume and fixed coefficient set form a bounded family, which is just a fancy way of saying that there exists a finite type variety with a family of pairs over it, so that every log canonical model with this volume and this coefficient set is a fiber of this family. And this is quite a deep result. I should say, how do you see this for curves? For curves, what do you do to get boundedness? Well, what you do is you say, well, I have my log canonical divisor, it's ample. And now you can use Riemann-Roch and standard duality to show that some fixed multiple of the log canonical divisor induces an embedding into projective space. If I have a fixed multiple that's uniform, that doesn't depend on which particular curve and which marked points I've picked, then I've put all my curves inside of a fixed projective space with fixed degree, and then we use results of growth index, which says that if you look at all n-dimensional subvarieties of fixed degree of a fixed projective space, they're parameterized by a finite type Hilbert scheme. And there we go. We've produced the finite type family because we put them all inside of the same projective space. So roughly, that's the type of result you need for boundedness. You need to prove some effectivity on the multiple that you need to multiply your ample divisor by to actually get an embedding into projective space. But of course, it's much harder in higher dimensions than it is for curves. Okay, so that's boundedness. So then 3, properness. This was the motivation for introducing semi-log canonical pairs. And this was first observed by Kolar and Shepard-Barron. So if you allow semi-log canonical stable pairs as well, I don't know why I'm repeating since stable pair includes semi-log canonical, but that's okay. Then the functor slash moduli space is proper. And what's the point here? So if we look at the valuative criterion for properness, what does this say? This says that all limits exist and are unique. So of course, we already talked about uniqueness in step 1. So once we have separated, then to get proper, we need to know that all limits exist. So what exactly does that entail? Well, if we have some, let's say, imagine the case of surfaces. If you have some family of log canonical models of surfaces, and they're all normal, and now you want to know the limit. So you have some family over a curve, say over a DVR. That's a valuative criterion. We have a family of log canonical surface pairs over a DVR that are stable, and we want to know that we can fill in the central fiber with something. And the claim is that the thing that you can fill in the central fiber with is exactly a semi-log canonical pair. And how do you prove that? Well, you say, let me fill in the fiber with something. Now I want to be able to control the singularities of the fiber, of the central fiber. The only way we know to control the singularities of a divisor inside of some ambient variety is to put that divisor with coefficient 1, and now a junction lets us control the singularities. So I take my family of surfaces, which is a threefold. I close it up into some threefold. So I guess I should write this. So we take x0 to c0 is some. So c is spec of a DVR. And this is some family of log canonical models in dimension n. So then x0 is n plus 1 dimensional. And I have maybe some boundary divisor here. And so x0 d0 is n plus 1 dimensional, but it's an n plus 1 dimensional relative log canonical model. So it's an LCM over C0. And so now what do? You say, well, let me close this up into some x, whatever it is. So in the case of surfaces, x is some threefold. In general, this is some n plus 1 fold. It has a central fiber, x0. If we take the close point, we get some x0. And now we want to control the singularities of x0, because if we allow arbitrary singularities, we're not going to get a bounded family. Because the singularities can just get worse and worse. The only way we know to control the singularities is with a junction. So to apply a junction, we need to add x0 as part of our boundary divisor. So now the upshot is we consider x comma delta plus x0. where delta is just the closure of delta 0. And now this is some pair, it might have very bad singularities. But we can still define its law canonical model, roughly by resolving singularities. There's a base change here that I don't want to get into in this class that you might have to do, but yeah, I just don't want to get into that in this class. And then we have this new pair. We add the right coefficients to the exceptional divisors of our resolution, and then we want to take the law canonical model relative to C of that pair. So we input this, we resolve and apply MMP, and produce a law canonical model of X delta plus X0 over C. And now, because of uniqueness of law canonical models, if they exist, then this law canonical model automatically satisfies the validative criteria of properness, because we want to show that limits exist and that limits exist and are unique. So if we know the law canonical model over C exists, then we get both existence and uniqueness for free. And so that was kind of the observation that to get properness, you need to be able to apply this procedure, and you need to run the relative MMP for this closure over your DVR. And now, once we do this, we get our new pair X prime delta prime plus X0 prime, our law canonical model. And now by adjunction, plus this observation previously that if you have a Cartier divisor, then it's automatically S2. This theorem of Alexeyev. So here, this X0 prime is Cartier because it's the fiber over a map to a curve. So it's the pullback of a point on a curve, and a point on a smooth curve is Cartier. So X0 is Cartier. So then by adjunction, X0 prime with its different, which is our limit, which is the limit of our family over our DVR, is semi-law canonical. And in fact, it's actually stable because we've taken the relative law canonical model, and so our law canonical divisor is ample relative to the base. And so when we restrict it to a fiber to get the canonical divisor of the fiber plus the different, then we actually get an ample law canonical divisor. And so this tells us that if we want a proper moduli space, then minimal model program suggests that we should look at the moduli space of stable pairs. So the upshot is that stable pairs form a proper moduli space. And I should put some names here. So this observation that this is what you should do was first observed by Kolar and Shepard-Barron, and they carried this all out in the case of surfaces, because then you need MMP for threefolds, and MMP for threefolds was known much earlier. And then Alexeyev built upon this work for surfaces, and so sometimes people call these KSBA stable pairs for their names. And then in higher dimensions, of course, we need BCHM, and this exact argument about being able to take these closures, I believe, is in a paper of Haken and McKernan. No, Haken and Shu, sorry. Called Existence of Law Canonical Closures. Again, building off of the BCHM results. I just want to make sure that I got that right. That there aren't, yeah, it's just Haken and Shu for this paper. Okay, and of course, tons of other work in between these things, but at least the MMP portion and this notion of semi-law canonical singularities came from this work. Okay, and finally, projectivity of the coarse moduli space. So here, I won't say too much about this, but the methods that come up for projectivity. So for the moduli space of curves, projectivity was originally is kind of done ad hoc by constructing the moduli space in a different way, not using this construction, but using GIT. And then whenever you have some GIT, some geometric invariant theory problem, there's conditions to check that it's projective. But that won't work in general for stable pairs. So you need some other methods, and the methods were developed by Kolar. The idea is that how do you show that something's projective? Well, you want to produce an ample line bundle. How do we produce an ample line bundle on our moduli space? Well, what we know about our moduli space is that it has a family of stable pairs. So we want to produce a line bundle. What's the only natural line bundle we have? It's the law canonical divisor, or the multiple of it, the plurilaw canonical line bundle for our family of stable pairs. But this is some relatively ample divisor. And so what you want to do is you want to push it forward, maybe take some large enough multiple, push it forward, study the behavior of those push forwards on the moduli space, and hope to use them to produce an ample line bundle on the moduli space. And so Kolar developed some general techniques to do this in this paper, Projectivity of Complete Moduli. And then these techniques were finally successfully applied. So this was in the maybe late 80s, early 90s, say around 1990. And then quite recently, Kovac and Patakfalvi actually carried out these techniques for the moduli of stable pairs in general. I forget the name of the title, but the name of the paper, but carried this out for. Okay, and so the upshot theorem, due to the combination of all of these names plus many more that have worked on the minimal model program and other things related over many, many years, is that stable pairs of fixed volume and coefficient set form a proper moduli space with projective coarse moduli space. And in the last like 30 seconds, I'll say the one thing that I haven't discussed at all and purposely skipped is actually the moduli functor. So for the case of curves, the moduli functor is just flat families of curves. What does it mean to have a family of curves? It just means you have a morphism where the fibers are curves and the morphism is flat. And this in this higher dimensional case, so families of stable pairs are not the same as just flat families with fibers being stable pairs. There are quite a few subtleties, and if you want to get into the subtleties, you can look at the book on Kolar's webpage, which is something like Moduli of Varieties of General Type.